So we've now reached section 3.4, which has to do with proving theorems involving sets. Some of these statements that we're going to prove here seem obvious, especially if you draw a Venn diagram, but they require proof even if they seem obvious. And the way that we're going to prove them is really just an exercise in knowing the definitions of all these various set operations and set relationships. So we're going to start off by doing an example of how to prove that some set A is a subset of a set B. And the definition that we gave of A as a subset of B is that every element of A has to also be an element of B. We can write that using our logical language as, for every x in our universe, if x is an element of A, then x is an element of B. So essentially, to prove that A is a subset of B, this is the statement that we're trying to prove is correct. This is a universal quantifier at first. And the way that we prove a statement with a universal quantifier is we let x be an arbitrary member of our universe, assume that x is an element of A, and then show that x is an element of B. Remember, this is essentially a conditional statement inside the parentheses here. If x is an element of A, then x is an element of B. So to prove that directly, we assume the hypothesis and we prove the conclusion. All right, so these are our two steps. First, let x be some arbitrary element of the first set. Then use our known results and definitions to show that x is also an element of the second set. Right, this is basically assume the hypothesis that x is an element of A, prove the conclusion that x is an element of B. All right, now these sets are gonna, be a little bit more complicated than just A and B, and so let's do an example. So let A and B be arbitrary sets. We're going to show that no matter what these sets A and B are, we'll always know that the set A minus B is a subset of the set A union B. Now let's try and convince ourselves this is true using just Venn diagrams here. Here's A, here's B. And let's just remind ourselves, what is the set A minus B? So A minus B is all the stuff that's in A and not in B. So it's this sort of half moon shape area of the Venn diagram right here. This red part is A minus B. And what is the set A union B? Well, this is all of A and all of B, just squished together into one big set. So this green part is A union B. It seems pretty clear from the picture that A minus B, the red shaded region, is a subset of A union B, the green shaded region. But if it's obvious, we should be able to prove it using our definitions. So that's what we're going to do here. So let's follow these steps. So the first thing we're going to do is let x be an arbitrary element of the first set. So up here our first set was just A, but in this example our first set, the left-hand side, is the set A minus B. All right, so let's let x be an element of A minus B. We need to prove that x is also an element of the second set, right? The second set up here was just B. In our example, the second set would be A union B. This is just sort of a very rough outline of what our proof should look like. We need to do the justification in the middle in order to conclude that x is an element of A union B. But that justification is really just unpacking definitions. And so what we start with is the fact that x is an element of A minus B. This is set difference here. And so we should be able to break this down a little bit using the definition of set difference. By definition of set difference, we have that if x is an element of A minus B, that means that x is an element of A and x is not an element of B. This is how we define the set A minus B. It's the stuff that's in A and not in B. So x is an element of A and x is not an element of B. Now what are we trying to show? We're trying to show that x is an element of A union B. Well, we need to justify that x is an element of A union B, so we should be thinking, what does it mean to be an element of A union B? By our definition of union, it means that x is an element of A or x is an element of B. That's an or statement, so as long as at least one part is true, as long as x is an element of A or x is an element of B, then we're done. We can conclude that it's in the union. And it is, right? It's an element of A. We know that by the definition of set difference. So since X is an element of A, it follows that X is an element of A or X is an element of B. Why? Well, because to satisfy this OR statement, you just need one of these things to be true, and we know that the first one is true. Therefore, this OR statement is true. And now we can say by the definition of set union, it follows that X is an element of A union B. Because this right here is the definition of set union. This is what it means to be an element of the union of A and B. And that's it, right? We've done the two steps that we needed to do. We let X be an element of the first set, and we explained why that means X is an element of the second set. So we now wrap up our proof and say, thus, A minus B is a subset of A union B. Okay, so we'll see some more examples of proving one set is a subset of another in the exercises. For now, I also want to talk about how do we show that two sets are equal. In fact, this is just an extension of what we did in the last example, because the definition of A equals B is as follows. It says, for every X and for every Y, if X is an element of A, then X is an element of B. In other words, this statement is basically saying that A is a subset of B. And for every Y, if Y is an element of B, then Y is an element of A. Well, this is just saying that B is a subset of A. So to prove that A and B are equal to each other, we need to show that A is a subset of B and that B is a subset of A. Well, that just means we need to do the steps that we did in the last proof twice. First, show that A is a subset of B. And we know from the last example that to do this, we let X be an arbitrary element of the first set, A, and prove X is an element of the second set, B. Then we need to show that the reverse inclusion is true. We need to show that B is a subset of A also. I don't want to use the same variables, so I just chose a different variable Y. We're going to say that let Y be an element of B, and then we're going to explain why Y must be an element of A. Right? So we're going to use this to try and prove that A minus B is equal to A intersect B complement. All right, so let's try and convince ourselves that this is true. I'm going to do a Venn diagram. I'm going to highlight A minus B, just like last time. This looks like this sort of half moon region over here. Take all of A and subtract the stuff that's in B. Now I'm going to do another Venn diagram and highlight A intersect not B. All right, this is an intersection, so I want to find the stuff that's in A and also not in B. So let me start off by shading A. That's all of A. Now I'm also going to highlight the stuff that's in not B, in other words, everything outside of the B circle. And then I'm going to look for the overlapping part. Where do these two sets overlap? Where does the red shaded region overlap with the purple shaded region? And the only place that that happens is exactly here. Right? That exactly is the place where you have elements that are in A and not in B. So this certainly seems to be true that these two sets are equal to each other. If we look at the shaded regions for both, they look the same. And so this seems like it's true, but you need to prove it using the definitions. It's not enough to do a Venn diagram. So let's try to use these steps to prove that A minus B is equal to A intersect B complement. All right, proof. Well, let's walk our readers through our plan here. To show two sets are equal, you need to show that the first set is a subset of the second set. We must show that A minus B is a subset of A intersect B complement. And then we need to show the reverse of that, right? That the second set is a subset of the first set. A and B complement is a subset of A minus B. Okay, so 1. We're going to prove that A minus B is a subset of A intersect B complement. The way that you do that is you let X be an arbitrary member of the first set, that is, let x be an arbitrary member of A minus B, and then prove that x must also be an element of the second set. Prove that x is also going to be an element of A intersect B complement. So we let x be an element of A minus B. We will show x is an element of A intersect B complement. Just like last time, we can unpack this using the definition of set complement. By the definition of set complement, we have that x is an element of A and x is not an element of B. Now we're trying to show that x is an element of A intersect B complement. Okay, so I know that x is an element of A, which is good news, but I also need to show x is an element of B complement. That's almost what I have, but what I have is that x is not an element of B. That's exactly what it means to be an element of B complement, but we need to walk our reader through that reasoning there. How do we know that this means the same thing as this? That's just the definition of set complements. So by the definition of set complement, sorry, this was set difference on the last one, my bad. This is the definition of set difference here. And now by the definition of set complement, x and A, this is just the same, I'm just copying this from before, but I can rewrite x is not an element of B by saying x is an element of B complement. Okay, and now we're basically done, because to be an element of A and an element of B complement, it means you're in the intersection of those two sets. So by the definition of set intersection, this means that x is an element of A intersect B complement. That's exactly what we were trying to show. So we're done with this direction of the proof. Thus, A minus B is a subset of A intersect B complement. That's halfway. We're almost done. Now the other way. All right, now we're going to let y be an arbitrary element of this first set. Let y be an element of A intersect B complement. And we will show that y is going to be an element of the second set. That y is an element of A minus B. As it turns out, this is going to be really the same reasoning, just going the other way. Essentially, we're just reading these reasonings off backwards. All right, we have that y is an element of A intersect B complement. By the definition of set intersection, this means that y is an element of A and y is an element of B complement. Okay, we're trying to get to A minus B, so let's turn this statement here into a statement that doesn't have a B complement and instead has a B. That's just the definition of set complement. We can conclude that y is an element of A and y is not an element of B. And now by the definition of set difference, if it's in A and it's not in B, that means it's in A minus B. Y is an element of A minus B, which is exactly what we were trying to prove. Thus, A intersect B complement is a subset of A minus B. That's it, right? Those are the two things we had to prove. I'm just going to wrap up this proof with a concluding sentence. Since each set is a subset of the other, we can conclude that these sets are equal. That is, A intersect B complement is equal to A minus B. All right, so you'll see that a lot of these proofs, they start off with the same basic structure. Let x be an element of one set, we're going to show it's an element of another set. And all this stuff in between, for the most part, it's just unpacking definitions. Right, you need to know these definitions really carefully. So in class, we're going to have some exercises where we just rewrite statements in various formats using various definitions. Go back and review those definitions in the notes. If any of these don't look familiar, you're going to want to know these a little bit more carefully. All right, so we're going to do one more example together. This one, oh boy, this one seems so obvious. Why would you even need to prove this? Let A and B be arbitrary sets, then A union B is equal to B union A. Right? I don't even want to draw them in diagrams. You know what they look like. You're just shading both A and B. So of course these should be equal. But if it seems obvious, we should be able to prove it without much trouble. So let's do this one together. Proof. Now this is set equality. When you see that equal sign, you should be thinking to yourself, I have to prove two things here. Right? I have to prove one's a subset of the other and vice versa. We must prove A union B is a subset of B union A, and vice versa. B union A is a subset of A union B. Right, that's what you should be thinking to yourself. So I'm going to just do that a little bit more carefully down here. We will prove A union B is a subset of B union A, and 2, B union A is a subset of A union B. All right, how are we going to do that? Let's start with this one. To prove one set is a subset of another, you let X be an arbitrary element of the first set and then explain why X is an element of the second set. Let X be an element of A union B. We will show X is an element of B union A. Okay, well, let's unpack this using the definition of set union. This means X is an element of A or X is an element of B. Okay, now what are we trying to show? We're trying to show X is an element of B union A. In order for this to be true, in order for X to be an element of B union A, that means it's an element of B or it's an element of A. That's basically what we have here, but in a different order. So how do we know, how do we justify that this means the same thing as the swapped version of this, that X is an element of B or X is an element of A? And you may have forgotten this by now, it was so many videos ago, but we really justified this way back when, in chapter 1, when we looked at all the different properties of our logical connectives. Right? We proved using truth tables, or if we didn't, then we at least alluded to such a proof with a truth table, that the statement P or Q is logically equivalent to the statement Q or P. This is super simple to prove in a truth table. All right? And because these statements are logically equivalent to each other, these are statements too, right? This is maybe your P and this is your Q, and that's logically equivalent to Q or P. So we call this commutativity of statements. Commutativity of what we call these disjunctions, because they're or statements. We have that X is an element of B, or, X is an element of B, or X is an element of A. And now that I have it in that reverse order, okay, that's what it means to be an element of the union. So one more time, by the definition of union, this means X is an element of B union A. Thus, we started with an element of A union B, we explained why it's an element of B union A. That means that A union B is a subset of B union A. Okay, that's one direction of the proof. Now we have to do the other direction of the proof. Let Y be an element of the second set, B union A. We will show that Y is an element of A union B. Well, guess what? It's the exact same steps, but backwards. In fact, for a proof like this, where what you're proving is so basic, it's really just using the definition of union and then the fact that or statements are commutative. You don't even really need to do both of these arguments. You could do it once with just if and only ifs in between. So we would say X is an element of A union B, if and only if X is an element of A or X is an element of B by the definition of set union. if and only if X is an element of B or X is an element of A by the commutativity of disjunction. If and only if X is an element of B union A by the definition of union. So I'm sort of doing more work than I really have to do. Well, we can maybe do an example in class where I omit the second half of the proof by doing the entire thing using if and only if statements. But we're still getting into the groove of doing these proofs, so I'm gonna leave it with this extra step for now of proving the other way. All right, but let's just do this again. By definition of union, this means Y is an element of B or Y is an element of A. Now we can swap those two around using the commutativity of disjunctions, or the commutative property of disjunctions, to say that this means Y is an element of A or Y is an element of B. And now using the definition of union again, we have that Y is an element of A union B. All right, so we started with an element of B union A, and we justified why it's an element of A union B. Thus, B union A is a subset of A union B. And again, let's wrap this up with a concluding statement. Since each set is a subset of another, they are equal. That is, A union B equals B union A. So we'll get some practice with rewriting these definitions in class today and really practicing what it means to set up a proof of subset, either the subset relationship or set equality. And then for our next class, we'll do a lot more examples of actually writing these proofs.